Are for loops in pandas really bad? When should I care? Are for loops really bad? If not, in what situations would they be better than using a more conventional vectorized approach? 1. I am familiar with the concept of vectorization, and how pandas employs vectorized techniques to speed up computation. Vectorized functions broadcast operations over the entire series or data frame to achieve speedups much greater than conventionally iterating over the data. However, I am quite surprised to see a lot of code, including from answers on Stack Overflow, offering solutions to problems that involve looping through data using for loops and list comprehensions. The documentation and API say that loops are bad, and that one should never iterate over arrays, series, or data frames. So, how come I sometimes see users suggesting loop-based solutions? While it is true that the question sounds somewhat broad, the truth is that there are very specific situations when for loops are usually better than conventionally iterating over data. This post aims to capture this for posterity.
TLDR, no, for loops are not blanket bad, at least, not always. It is probably more accurate to say that some vectorized operations are slower than iterating, versus saying that iteration is faster than some vectorized operations. Knowing when and why is key to getting the most performance out of your code. In a nutshell, these are the situations where it is worth considering an alternative to vectorized pandas functions. When your data is small, depending on what you're doing. When dealing with object/mixed types. When using the str/regex accessor functions. Let's examine these situations individually. Iteration vs vectorization on small data. Pandas follows a convention over configuration approach in its API design. This means that the same API has been fitted to cater to a broad range of data and use cases. When a pandas function is called, the following things, among others, must internally be handled by the function to ensure working. Index/axis alignment. Handling mixed data types. Handling missing data. Almost every function will have to deal with these to varying extents, and this presents an overhead. The overhead is less for numeric functions, for example, series.add, while it is more pronounced for string functions, for example, series.str.replace. For loops, on the other hand, are faster than you think. What's even better is list comprehensions, which create lists through for loops, are even faster as they are optimized iterative mechanisms for list creation. List comprehensions follow the pattern where sec is a pandas series or data frame column, or when operating over multiple columns. Where sec1 and sec2 are columns. Numeric comparison. Consider a simple Boolean indexing operation. The list comprehension method has been timed against series.ne, not equal, and query. Here are the functions. For simplicity, I have used the puffplot package to run all the time-eat tests in this post. The timings for the operations above are below. The list comprehension outperforms query for moderately sized n, and even outperforms the vectorized not equals comparison for tiny n. Unfortunately, the list comprehension scales linearly, so it does not offer much performance gain for larger n. Note: it is worth mentioning that much of the benefit of list comprehension come from not having to worry about the index alignment, but this means that if your code is dependent on indexing alignment, this will break. In some cases, vectorized operations over the underlying NumPy arrays can be considered as bringing in the best of both worlds, allowing for vectorization without all the unneeded overhead of the pandas functions. This means that you can rewrite the operation above as value counts. Taking another example, this time, with another vanilla Python construct that is faster than a for loop, collections.counter. A common requirement is to compute the value counts and return the result as a dictionary. This is done with value_counts, np.unique, and counter. The results are more pronounced. Counter wins out over both vectorized methods for a larger range of small n, tilde 3500. Note: more trivia, courtesy at user 2357112. The counter is implemented with a accelerator, so while it still has to work with Python objects instead of the underlying C data types, it is still faster than a for loop. Python power. Of course, the takeaway from here is that the performance depends on your data and use case. The point of these examples is to convince you not to rule out these solutions as legitimate options. If these still don't give you the performance you need, there is always Python and Number. Let's add this test into the mix. Number offers JIT compilation of loopy Python code to very powerful vectorized code. Understanding how to make Number work involves a learning curve. Operations with mixed/object types. String-based comparison. Revisiting the filtering example from the first section, what if the columns being compared are strings? Consider the same three functions above, but with the input data frame cast to string. So, what changed? The thing to note here is that string operations are inherently difficult to vectorize. Pandas treats strings as objects, and all operations on objects fall back to a slow, loopy implementation. Now, because this loopy implementation is surrounded by all the overhead mentioned above, there is a constant magnitude difference between these solutions, even though they scale the same. When it comes to operations on mutable/complex objects, there is no comparison. List comprehension outperforms all operations involving dicts and lists. Accessing dictionary values by key. Here are timings for two operations that extract a value from a column of dictionaries, map, and the list comprehension. The setup is in the appendix, under the heading Code Snippets. Positional list indexing. Timings for three operations that extract the 0th element from a list of columns, handling exceptions, map, str.get, accessor method, and the list comprehension. Note if the index matters, you would want to do. When reconstructing the series. List flattening. A final example is flattening lists. This is another common problem, and demonstrates just how powerful pure Python is here. Both itertools.chain.from_iterable and the nested list comprehension are pure Python constructs, and scale much better than the stacked solution. These timings are a strong indication of the fact that pandas is not equipped to work with mixed types, and that you should probably refrain from using it to do so. Wherever possible, data should be present as scalar values, ints/floats/strings, in separate columns. Lastly, the applicability of these solutions depend widely on your data. So, the best thing to do would be to test these operations on your data before deciding what to go with. Notice how I have not timed apply on these solutions, because it would skew the graph. Yes, it's that slow. Regex operations, and .str, accessor methods. Pandas can apply regex operations such as str.contains, str.extract, and str.extractl, as well as other vectorized string operations, such as str.split, str.find, str.translate, and so on string columns. These functions are slower than list comprehensions, and are meant to be more convenience functions than anything else. It is usually much faster to precompile a regex pattern and iterate over your data with re.compile. Also see is it worth using Python's re.compile. The list comp equivalent to str.contains looks something like this. Or if you need to handle nar-ns, you can do something like the list comp equivalent to str.extract, without groups, will look something like. If you need to handle no matches and nar-ns, you can use a custom function, still faster. The matcher function is very extensible. It can be fitted to return a list for each capture group, as needed. Just extract query the group or groups attribute of the matcher object. For str.extractl, change p.search to p.findl. String extraction. Consider a simple filtering operation. The idea is to extract 4 digits if it is preceded by an uppercase letter. More examples. Full disclosure, I am the author, in part or whole, of these posts listed below. Fast punctuation removal with pandas. String concatenation of 2 pandas columns. Remove unwanted parts from strings in a column. Replace all but the last occurrence of a character in a data frame. Conclusion? As shown from the examples above, iteration shines when working with small rows of data frames, mixed data types, and regular expressions. The speed up you get depends on your data and your problem, so your mileage may vary. The best thing to do is to carefully run tests and see if the payout is worth the effort. The vectorized functions shine in their simplicity and readability, so if performance is not critical, you should definitely prefer those. Another side note, certain string operations deal with constraints that favor the use of NumPy. Here are two examples where careful NumPy vectorization outperforms Python. Create new column with incremental values in a faster and efficient way, answer by Divakar. Fast punctuation removal with pandas, answer by Paul Panzer. Additionally, sometimes just operating on the underlying arrays via dot values, as opposed to on the series or data frames, can offer a healthy enough speedup for most usual scenarios. See the note in the numeric comparison section above. So, for example, df.a.values not equal df.b.values would show instant performance boosts over df.a not equal df.b. Using dot values may not be appropriate in every situation, but it is a useful hack to know. As mentioned above, it's up to you to decide whether these solutions are worth the trouble of implementing. Appendix, Code Snippets. Less than dash. 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 Less than, underscore greater than.
In short, for loop plus iteros is extremely slow. Overhead is insignificant on 1k rows, but noticeable on 10k plus rows. For loop plus itertuples is much faster than iteros or apply. Vectorization is usually much faster than itertuples. Benchmark.
If you want to see more, please consider subscribing.